Hello, everyone. I'm Mohammad Asif Khan from Qatar Mobility Innovation Center, and I'm presenting my work on curriculum for crowd counting. Is it worthy? My co-authors include Dr. Hamid Munawwar and Professor Rida Hamila. So crowd counting is an interesting problem in computer vision, which aims to count or estimate the number of objects of interest that can be people, cars, or any other kinds of objects inside an image or a video frame. The de facto and most widely used method for crowd counting is density estimation, which uses convolution neural networks or CNNs. Density estimation is actually a pixel-wise regression method used for crowd counting, and CNN so far outperforms all other techniques and density estimation methods, including the vision transformers, which have been recently introduced for computer vision tasks. This figure shows how we can use a CNN model in the density estimation method for crowd counting. So in crowd counting, we always take annotated images where the annotation or ground truth is a density map of the crowd. The density map actually shows the head positions of the persons inside the image. And once the model get trained, it is exposed to unseen images to predict a similar kind of density map. The pixel values of the predicted density maps are then integrated to get the total count of the people inside the image. Here are, in this table, we can see some of the representative works on crowd counting over the last couple of years, starting from 2015, which was the first CNN-based crowd counting architecture, until 2022. Now, in this table, you can see some of the model-centric approaches which mainly involve architectural innovations in the CNN network architecture. However, we are more interested to see if we can have some data-centric approach to improve the performance of these existing CNN models for crowd counting. One of the technique that can be used for improving the performance of crowd counting is curriculum learning. Curriculum learning is actually a human-inspired training method in which the training data is organized in a meaningful order, typically in the order of increasing or decreasing complexity of the samples or the images in the data set before we expose this data to the model to get trained. This technique was proposed or formalized by Benji et al. In 2009. This figure shows how curriculum learning works. So as you can see in this figure, we take a full data set in which the training samples are unsorted. They are randomly arranged. We apply a scoring function which actually organize the samples in particular order, typically by increasing or decreasing difficulty or complexity to get the sorted data set here. Then we take a pacing function, and the pacing function actually samples the full sorted data set to get mini batches of the mini batches of the data. And each mini batch is then applied in each iteration of the training to train the model. And in this way, the model is exposed to the model to the sorted data in a particular fashion. This on the top, we can see the mathematical representation of curriculum learning. Typically, we can achieve two benefits from curriculum learning. First, we can train the model, and the model can converge much faster than the standard training. And second, we can get higher accuracies using curriculum learning than the standard training. Now, in this work, we are attempting to address three research questions. Number one, does curriculum learning outperform standard training in crowd counting? Number two, how much is the performance gain that can be achieved using curriculum learning? And number three, what are the factors that can impact the performance of curriculum learning in crowd counting applications? We conducted a number of experiments, a total number of 112 experiments using 6 different curriculum learning settings and 8 different crowd counting models. We used Shanghai Tech Part A and B data sets in this study, And all the models are trained using PyTorch framework on two RTX 8000 GPUs. The metrics being used for the evaluation of the crowd models are mean absolute error and mean squared error, and the equations for these metrics are given on this slide. This slide shows the results that we achieved for our experiments. Now, you can see here the first and leftmost columns are the mean absolute error and mean squared error for standard training, and all the other remaining columns on the right side shows the results for curriculum learning using different pacing functions on these columns. The top column shows, the top table shows the results for Shingai Part B, and the second table shows for Part A dataset. Now the results in the red boxes are actually the best results that have been achieved or different models and different pacing functions. And one observation that you can note here is that mostly the curriculum learning outperforms the standard training in these experiments. This figure on the right side shows how curriculum learning converges as compared to the standard training, and you can see the sample size, the same number of samples being used for the training on the x-axis. So the down x-axis shows standard training, and the top x-axis shows the curriculum learning. And here you can note that just with very few training samples as compared to the standard training, curriculum learning can converge much faster than standard training method. Now, here are some of the discussions and conclusions from these experiments that we have performed. So first, we can see significant gains in some cases using curriculum learning, while we get marginal gains in most cases using curriculum learning, while some cases also shows almost no gains in using curriculum learning, and the results were quite similar to standard training. We conclude that curricular learning can potentially improve the accuracy by carefully choosing or configuring the pacing function, which is an important hyperparameter in curriculum learning settings. However, we are pretty sure that curriculum learning is a very good choice to cut the convergence time in most applications. As a future work, we aim to extend these evaluations to other computer vision tasks using larger data sets and different scoring functions that are appropriate to the task being done. Thank you so much for listening. And if you have any question, please don't hesitate to write to us using this email address.